As we have seen in the last session, we showed you some videos of typical photoelastic fringes, and the first thing that anybody would notice when you look at some of these fringes is the fact that they all look rainbow colored, right. And so the word rainbow naturally raises the question of where these fringes are coming from, and it is not surprising to know that they are related to the phenomenon that finally leads to a rainbow, which is refraction. And so to really understand where fringes are coming from, why some materials show fringes, some materials do not show fringes, in fact most materials do not show fringes. If you take a piece of metal or a piece of opaque plastic, you do not see any fringes there. But if you look at glass, various types of glass, if you look at transparent rubbers, transparent plastics, these do show fringes to varying degrees, of course varying intensity degrees. And so to understand why this is the case, we need to delve a little bit deeper into the nature of light itself, and so that is what we will do today. I will discuss some very basic ideas from a slightly different point of view. I am sure many of you have seen this in a 10th standard or a 12th standard physics textbook before. It is very elementary, but if you think a little bit more carefully, the exact reasons behind why some of these phenomena actually occur is perhaps not so trivial, and that is what we will discuss. So in order to understand the origin of fringes, we need to understand first the origin of refraction. Okay, why does refraction occur? We all know refraction, of course, we know Snell's law, you probably heard this multiple times before. We know how to calculate what happens when light is incident on a transparent object, what is the path that it finally takes, does it deviate away from the normal, towards the normal, sin theta, n, refractive index, all that stuff is known, right. So we know operationally what it is, but then do we understand where refraction comes from a microscopic point of view? Why do some materials refract light, why do some materials not refract light, and so on. So that is something we have to consider, and when we do this, we will very quickly realize that in addition to looking at the origin of refraction, we have to look at the origin of light itself. Okay, and this, I know this sounds melodramatic, but to understand why certain phenomena happen, you need to look at the wave nature of light, and if you go back to the beginning of the class and to what we have discussed so far, we have always been talking about light as being a ray, right. So far for us light is just a ray. When you draw a lens diagram, write thin lens equation and so on, you always draw a ray, right. But light is not just a ray, this is an approximation. So a light ray, the notion of a light ray is an approximation, and light is in fact, as we know, a wave, and it is not any wave, it is what is called an electromagnetic wave. I am sure you have seen this phrase also before, and you need to go back and look at what an electromagnetic wave is and why it does what it does when it interacts with materials, right. So it takes us into some fairly alien territory. We will try to cover that in as qualitative a manner as possible, and hopefully this will give you some background to help you understand why refraction occurs in the first place, and then from there we will step back and try and understand why birefringence, or rather the phenomenon that underlies photoelasticity, why birefringence turns up in many materials. So let us start with basic idea of an EM wave. Okay. So light is going this way, let us say this is the direction of propagation, and this is well known, right. I mean, if you have a light bulb, you know that is the origin of the light, right, because there is some filament, presumably if it is a tungsten filament light bulb, then the tungsten is getting heated up, it is emitting light, it is emitting photons, and they are all coming in a certain direction towards you. So the direction, if you approximate the light bulb as a point source, the direction of propagation is clear, right, it is coming from the source to you. But along each point of the propagation direction, there are actually two vectors, right. There is what is called an E vector and a B vector. The E is the electric field vector and the B is a magnetic field. So the electric field and the magnetic field are both always perpendicular to each other, and they are also always perpendicular to the direction of propagation. Okay, what this means is that at every point along the ray there is a field, an electric field, there is a magnetic field that is perpendicular to it, and these electric and magnetic fields are basically changing in time. Okay, so they are oscillating in time, and they are oscillating if you have a light wave in vacuum, let us say, without interacting with any material, then they are oscillating as they go along. The electric field is oscillating like this along the light, along the ray, and the magnetic field is oscillating, let us say, like this along the light. Okay. Now, the direction of oscillation of one of them, let us say E bar, just to keep things concrete, B bar is perpendicular always. The direction of oscillation determines what is called the polarization of light. Okay. And if light is plane polarized, that means that the direction of oscillation is always in one direction, so along one axis. If it is circularly polarized, the axis rotates in a circle, it is elliptically polarized and so on. So, we will give some details of that later on, but basically polarization is related to this direction of oscillation. Now, if you recall Snell's law for refraction, it tells you basically that if you have an interface, so this is an interface, and you have a medium 1 and medium 2, then light coming in like this is going to get refracted like this, and if you draw the normal to the interface, you call this theta 1 and you call this theta 2, this is the direction of propagation. Then Snell's law says that n1 sin theta 1 is n2 sin theta 2. Okay. And we all know that this n1 and n2, these are called the refractive indices of medium 1 and medium 2 with respect to air, right. You could take the ratio and then write n12 is n2 by n1 is the relative refractive index of medium 2 with respect to medium 1, right. So, this is standard Snell's law, again from 12th standard physics, you have probably seen this many times. So, what is the refractive index? Okay. That is the next question. So, we are going layer by layer, we are starting from what we know and then we are going into something that is reasonably unknown, at least to us. These phenomena are fairly well known, they have been known for several decades at least, but let us try and understand this in a sequential manner. So, what is the refractive index? Now, refractive index obviously is a dimensionless number, right, because sin theta has no dimensions, and so refractive index also is a dimensionless number, and it really is the ratio of the speed of light in one medium with respect to the other. Okay. So, this is what is called the absolute refractive index. So, this could be refractive index of glass in air, for example. C is the speed of light in vacuum. When I say air, I mean vacuum, air and vacuum are practically the same for all practical purposes, and this is 2.99 into 10 power 8 meters per second, and this is the velocity or what is called the phase velocity. I am going to put this in quotes, I will explain what phase velocity is in a minute. This is the phase velocity in the medium. Okay. So, the refractive index is the ratio of these two and its dimension is because both have dimensions of meters per second. So, usually for most materials, there are some exceptions, we will talk about them again a little bit later. Usually for materials, notice also the index I is for material I. So, if you have two materials and material 1 will have refractive index n1, corresponding phase velocity v1 and so on. So, usually Ni is greater than 1, okay, and this makes sense because speed of light in vacuum, as you have probably heard, is the fastest you can ever go. You can't go faster than that, at least information can't propagate faster than that, and usually Ni is greater than 1, but there are cases where Ni can be less than 1. It does not violate any principle of physics because you are talking about what is called the phase velocity, and I will explain this in a minute. Okay. There are cases where Ni is also negative. These are called negative refractive index materials. We will not talk about them, but they are an active area of research interest, and there are also situations where the refractive index is complex, okay, which has a certain implication which we will get to in due course, but this basically defines what the refractive index is, right. So, before we go further, we have to understand this idea of a phase velocity as opposed to what is called a group velocity. First, okay. Now, let us say I have a wave like this, it has a certain wavelength lambda 1, and then I have another wave which is like this and it has a wavelength lambda 2. Lambda 1 is obviously larger than lambda 2 as I have drawn it here. You can combine these waves and get a third wave which perhaps looks something like this. I am making this up, this is not the exact sum obviously because I am drawing it free handed. Now, this is obviously called the superposition of wave 1 and wave 2, this being wave 1, this being wave 2. And it turns out that for linear, what are called linear waves, any waveform, right, even if you have a wave that looks like this, you can break this into constituent single wavelength waves. So, for example, this fellow here, you can write this as this plus this plus this plus. So, these are all single wavelength waves. So, this is lambda 1, lambda 2, lambda 3 and so on, different amplitudes A3, A2, A1 and so on. So, you can break up any of these break up any such wave like this or any signal of this form into constituent waves. You might have a lot of constituent waves, but nonetheless it can be done in some very definite way. Okay. Now, if this wave had a speed c1, this wave had a speed c2, direction of propagation, which means that the time taken for this point, remember this, as the wave propagates, a point here is going up and down, and the time taken for that to do one full up and one full down and come back to its starting point is and that of course divided, the wavelength divided by the time is the wave speed c1, okay, and likewise over here. Now, if c1 is equal to c2, or indeed if in this case all ci's are equal, that means that the material or the wave or rather the material in which the wave is propagating is non-dispersive. So, a very simple thing that you can probably imagine is if you just take this example, the one we have drawn here, if you have C1 and C2 equal, then the speed at which this wave moves forward will also be the same as C1 or C2, right, because there is no change, everything is moving at the same speed, the wave will retain its shape and it will keep propagating at the same speed. Now, interesting things happen when this C, which I am going to call this, which I am going to give a subscript of P for phase, when this Cp of lambda is not constant, which means it depends on lambda. When this happens, then you have dispersion. Okay, so when the wave speed for the individual sinusoidal waves depends on the wavelength of that wave, then you have something called dispersion. Now to explain what dispersion is, I will show you a very short animation so that the idea is clear, and we will annotate on top of the animation. Okay, here are three panels showing you the difference between a group velocity and a phase velocity. So this is borrowed, the source is provided over here. You can easily make an animation like this in MATLAB or Python. It is very simple to do, you only need a suitable way to visualize final time dependent waveforms, but this is just one to illustrate the point. Now let me show you what these individual panels represent, but before that there are two dots that are marked in each panel. There is the red dot which represents the phase velocity, and there is a blue dot that represents the group velocity. Okay. So for example, if you take this panel, the red and the blue are always coincident because the phase velocity and the group velocity are the same. Okay, you can see that they are going together. The phase velocity and the group velocity not being the same, there are two simple cases that are illustrated here. So let us take the case where the group velocity is 0. Okay. The phase velocity tells you this, for example, if you see this red that is going here, that is following this trajectory, it tells you how that point at the same phase is moving, right. But if the group velocity, which is the added sum of everything, is unchanged, then the total envelope of the wave does not propagate, right. So if you look at this, the outline I have drawn here is stationary, even though stuff is wiggling inside, there is some change inside, the overall envelope is still in the same location, and that is because the group velocity is 0. Okay. On the other hand, if you do have a finite group velocity and the group velocity is lesser than the phase velocity, then this case will happen. So you see that the red spot moves faster than the blue spot, and the blue spot represents in some sense the speed at which the entire wave train is propagating. Okay. So the red is point on the crest in this case, on one crest, it does not matter which one, you could take anything and that will move with the same speed as the one shown here, and the blue is the what I will call the wave train motion velocity. Okay. So the first panel is a non-dispersive case. So if I took this waveform and I split it up into various components, various constituents, each of those constituents will move at the same speed. Okay. The second case is dispersive, the third case is also dispersive, it is an extreme case, it is a standing wave, the third one, because it is not propagating. But let us look at the second one. The second one is also dispersive, which means some frequencies or some wavelengths I should say will move faster than other wavelengths. Okay. Now if you go back to our discussion of what the refractive index was, you remember refractive index is C by Vi. In the case where the medium is dispersive, some wavelengths moving faster than other wavelengths implies that Vi is a function of lambda. So the refractive index will be a function of lambda. Okay. And this is precisely why you see dispersion in a prism, and the word dispersion comes from here of course, because it is all dispersive. If you take a prism and you put white light going through, remember white light is, there is no color called white, of course we have learned that in school. It is comprised of all possible wavelengths, so going from red all the way to blue and beyond and so on, and each of them, since this prism is dispersive, the medium is dispersive, the refractive index, the velocity with which each phase or each wavelength propagates is dependent on the wavelength itself, and so the refractive index is a function of the wavelength. And so remember, this is not norm, this is incident at some angle theta, and so the corresponding theta that you get will change depending on what wave you are looking at. Okay. So this is your red, blue, green, etc., will have different values of theta 2, let us call this theta 1. Theta 1 will obviously not be equal to theta 2 because the incidence is not normal to this edge, and of course the exact value of theta 2 will depend on lambda because n depends on lambda, or n2 rather in this case. Again, that is why you see breakup of colors when light passes through a prism, right. Okay. So, coming back to where we were, we know now that dispersion implies that the refractive index is a function of the wavelength, and so this means that the angle of refraction is a function of the wavelength, which means you will see a split in color. Okay. Now, this is fine, this makes sense, but the more fundamental question we want to ask first is, okay, the refractive index is a function of wavelength, but if refractive index is different from 1, right, if n not equal to 1, then the sin theta 1 or consequently theta 1 is not equal to theta 2 or sin theta 2. So, the next question we want to ask is, why does light bend? Why should it bend in the first place? Okay, refractive index is different, velocity is different, but why can't it just move slower, right. So, you could as well think of a situation where let us say I have my interface like this and you have incidence like this, and I am telling you that the light goes faster, let us say this is air, light goes faster here, and then this is glass, let us say, and light goes presumably slower in glass. Why can't it just continue going like this, but just go slower, right. So, in delta t, if light has moved this much here, why can't it just move this much in glass? The velocity is lesser, why should it bend, right. So, that is the next question we have to answer. Why does it have to do this and not this? Okay. And the reason we are asking this question is because it leads to this discussion of an ordinary or extraordinary ray which comes up in birefringence, and if you have this background it will make understanding that a little bit more easier. Okay. So, why does light bend? To appreciate why light bends, we have to first go a little bit more deeper and ask the question, how does light interact with matter? How does light interact with matter? Now, at the level at which we have been discussing so far, it just only thing that matters is n, and only thing that you see as a consequence is theta. But if you look at it a little bit more microscopically, so you have your piece of glass and you zoom in and you see what happens. Okay. Now, you will notice the following: the light wave that is coming in, of course, has its electric field in this direction and it is propagating in this direction. The magnetic field is into the screen, of course, that is, I am going to assume that we are not going to talk about the magnetic field now, because whatever we say for the electric field will apply analogously to the magnetic field as well. When the light passes through this material, what does the material actually have? So, these are, let us say, atoms. My idea of atoms, they are fairly cartoonish, but the atoms themselves have electrons around them, right. For glass, we know soda lime or inorganic glass is typically amorphous, and so it does not have a regular arrangement of atoms. Atoms are in a disordered state, so to speak. The collection of atoms is not on a lattice, but the presence of these electrons basically is primarily responsible, I should not say only responsible, for interacting with light. So, here is what happens: your light source comes like, your light ray wave comes like this, the electric field is like this, and remember that the electron is a charged particle. Okay. So, the moment the electron sees an electric field, it experiences a force which is charge times field, we know that. And so if the field is oscillating up and down, if the field is doing something like this, then the charge also starts doing this. Okay. Now this is, you can think of this by analogy with a system that you are probably more familiar with, which is you take a spring and a damper and you attach a mass. If you apply a force to this mass and you will get it to oscillate, the mass will start vibrating of course, but it will vibrate with a phase change, right. So, or a phase shift. And if you go back and try to work out this problem, it is not very difficult to do, you have probably done it before. The phase shift will depend on the ratio of the applied frequency and the natural frequency of the material, right, and that of course depends on the spring constant, it is altered by the damping coefficient and things like that. This is purely by analogy, the actual equations are much more complicated as you can imagine, but for a conceptual idea this serves fairly well. Now the same type of thing you could imagine happens to the electron, right, it goes up and down with some phase lag compared to the wave that is coming in. Now the moment the electron starts going up and down, it is an accelerating charge, okay, oscillating or accelerating charge. And if you have an accelerating charge, equation of electrodynamics tell us that the charge will emit radiation. So this will also emit its own electromagnetic waves. Okay. So what you actually see in the material in this region, what you actually see is the wave that was originally coming in, or the field that was originally coming in, plus the sum of all the fields that are generated by all the electrons that are there in all the atoms that are sitting in the material. Okay. Loosely again, this is a fairly simplified picture, but it is a reasonably accurate picture I would think. So the actual full field is not just the incoming wave which is passing through by itself, but also the emitted waves that are emitted waves, sum of all the emitted EM waves that are coming from all the electrons that are in the material. Okay. So naturally when you add these two, the final vector or the final E bar full as I have called it here has a phase difference with the original incoming E bar. We will call this phase difference delta. Okay. Now this phenomenon is the basis for many optical phenomena that you will see in nature. For example, if the delta is let us say around pi by 2, the phase difference between the incoming and the sum total that is coming out, that is in the material, then the wave inside moves slower. If the delta is pi, the phase difference is pi, then when the E bar that is coming in is at a maximum, then the E bar, what did I call it, E bar emit. When the incoming E bar is maximum, then if the phase difference is pi, the E bar emit is minimum. So when you add them up, they will cancel each other. Likewise when the E bar is minimum, the E bar emit is maximum, you add them up, they cancel each other, and so they will perfectly cancel out, and so the net E bar, the E bar full is very close to 0. Okay. This happens when okay, let me come back to when this happens after I discuss the third case. So, if you have delta equal to 2 pi, then the E bar full is greater than E bar, the magnitude is greater than E bar, the incoming E bar. So, the incoming wave is amplified by the material, right. So, you pass some wave and the material amplifies that and generates a larger amplitude wave. So, this is exactly what happens in a laser, by the way. Light amplification, so amplification comes from here, right. The case 2, so this is case 1, case 2 and case 3. In case 2, since the final field is 0, basically the light that you are sending in is completely getting absorbed by the material. So, it is fully absorbed. And what happens when the light is fully absorbed? You can't see the light that you have sent in, which means that the material is opaque. Whatever you have sent in is gone, it is not coming out from the other side. And when this happens, when the first case happens, then you have a transparent material and you have Snell's law. Okay, so, wave coming in becomes slower. So, you have a refractive index and you have Ni is equal to C by Vi and all of the stuff, all of the good stuff we discussed before. So, in general usually you will see a combination of 1 and 2. So, the angle typically delta is between pi by 2 and pi, which means some part of it is transmitted through, which means it is transparent, the material is transparent to that particular light, and some part of it is absorbed, right. So, the ratio of how close it is to pi by 2 or how close it is to pi tells you the relative absorption versus transmittance of the particular light in the particular medium. Good. Okay. So, we know that light gets absorbed or gets transmitted because the stuff that is being oscillated is in phase or out of phase with the original light that is incident on the material, right. But this still does not explain why light should bend. So, we go back to our original question. So, when delta is between pi by 2 and pi, let us say it is close to pi by 2, we forget about absorption for now. When delta is pi by 2, why does light have to bend? Okay. Now, there is a simple argument for, well, not for explaining this, but certainly to rationalize it, and that is based on Fermat's principle. So, Fermat's principle, it tells us that light travels along a path such that the travel time is minimized. If you are given a sequence of materials with different refractive indices and consequently different velocities, you can use Fermat's principle to determine what the direction of propagation will be. Okay. So, what we will do in the next session as we attempt to finally answer this question, why light bends and why different wavelengths bend differently, is we will apply this principle very quickly to light passing through an interface, and then we will see what the consequent picture is on the microscopic scale before we discuss birefringence.